Associate Professor Wouter Schellart has provided fundamental understanding on the evolution and dynamics of the solid Earth. His research breakthroughs have resulted in the development of a new global theory of Earth dynamics, describing how the size of subduction zones affects the Earth's evolution and geodynamics. His work has quantified energy dissipation and flow patterns in the mantle, has identified a global terrestrial reference frame for plate tectonics, and provides new understanding for the geological evolution of the Southwest Pacific, Western North America, and East Asia. So, Professor Schellart, congratulations, and I invite you to tell us about your work on control of subduction zone size on plate tectonics and mantle flow.
Well, thank you very much. I'd first like to thank the Academy for this great honor. It's a great honor to receive a medal named after such a famous Australian geophysicist. I'd also like to thank my colleagues, my students and my postdocs for all the interesting research endeavors we've been involved in. And finally, I'd like to thank my wife, Gerda, and my children, Felix, Nina, Maya, and Casper. I guess I'd like to thank them mainly for keeping me every day with both my feet on solid Earth, and I guess that's pretty appropriate since I'm a solid Earth geophysicist. Now, if you hear some mumbling at the back there, I guess I have to apologize. That might be one of my children, but they'll leave after this talk, so then they'll be quiet again. In any case, my passion is geodynamics, dynamics of the Earth and the evolution of the planet Earth, in particular focusing on subduction zones. Now, you might wonder why subduction zones are important. I'll come to what subduction zones are a bit later. A lot of geophysicists and geodynamicists think that subduction zones are one of the main drivers or the driver of convection in the Earth's mantle and the tectonics, the motion of the tectonic plates. They're very important in creating and destroying geochemical heterogeneity in the Earth's mantle and crust. They're responsible for the biggest earthquakes on Earth, such as Japan 2011 and Sumatra 2004, and also the major source of volcanism on this Earth. So they're, in that sense, quite significant. Now, if we look at this map here, we see a global bathymetric and topographic map of the Earth. What is so nice about these maps nowadays? They're so high resolution that we can easily outline all the boundaries of the tectonic plates. So the Earth is covered with tectonic plates, about 15 big ones, more than 30 smaller ones, and they all move relative to one another at centimeters per year. Now, we have three types of plate boundaries, so the boundaries where the plates meet. We have in red divergent plate boundaries where the plates move apart. In brown we have transform plate boundaries where the plates slide past one another. And then in blue we have the convergent plate boundaries where the plates come together. And we have two types of convergent plate boundaries. We have collision zones where two continents come together and collide, forming things such as the Himalayas. And we have subduction zones, and this involves at least one oceanic plate, and the oceanic plate sinks below the other plate into the mantle. Now we can have a look at one example here, cross-section from the Southwest Pacific, where we see the Pacific plate subducting below the Australian plate at the Tonga subduction zone. Now this is a seismic P-wave tomography image showing in blue more or less the outline of the subducting Pacific plate. And you also see those dots, they represent earthquakes in the deep mantle, and they also represent the location of this subducting plate. Now this is obviously a snapshot of a nowadays subducting plate in the mantle. Now what geodynamicists and tectonicists are interested in is how do plates actually sink into the mantle, the kinematics and the dynamics of the sinking. Now when plate tectonic theory was developed in the 60s, initially it was thought that a plate sinks more or less down dip, parallel to its own dip plane into the mantle, and this means that the subduction zone plate boundary, the trench here, the deep sea trench, is more or less fixed in space. Now, if this is the case, a plate sinks down dip along its own plane, it creates a flow in the mantle, it stirs the mantle, and it creates two types of flow cells, two colloidal flow cells, where flow is oriented around a horizontal axis, one in the mantle wedge, what we see here, and one in the subslab region. Now, what a famous geophysicist named Wouter Schellart already discovered in 1971, so a few years after plate tectonic theory was developed, he noticed that subduction zones are actually not stable features in the mantle. The subduction zone plate boundary actually migrates with time. So he noted that as the slab sinks into the mantle, it's more buoyant, it's more dense than the ambient mantle, so it sinks backward through time. And we see as the slab falls back through the mantle, the trench here migrates backward with time as well. So the slab falls back through the mantle, and this has an important implication for flow in the mantle. As the slab falls back through the mantle, it has to displace mantle from below the slab towards the mantle wedge, and this occurs in a toroidal fashion. So material flows around the slab edges into the mantle wedge, and it occurs in a toroidal fashion where flow is oriented around a vertical axis. Okay, as I said, tectonicists and geodynamicists are interested in the motions of the plates and the plate boundaries and the forces that cause these motions. So here we see a nice example of the South American region where we have a subducting plate called the Nazca plate moving at about 7 centimeters towards the east below the overrunning plate, the South American plate. But the South American plate is only moving about 1.5 centimeters a year. So the question, why is this the case? What we also see here, these red numbers you see over here, they indicate the velocity of the plate boundary in centimeters per year. And what we see is that the plate boundary, the subduction zone plate boundary only moves about 3 millimeters up to about 1.6 centimeters a year. If we look at another subduction zone here in the south, the Southern Atlantic, the Scotia subduction zone, here we have the South American plate subducting below the Scotia plate, and here we see quite the opposite. We see the subduction zone trench, indicated by this red arrow, moving eastward about 6 centimeters a year. So the plate boundary is moving eastward at 6 centimeters a year, but the subducting plate, which in this case is the South American plate, is moving into the subduction zone only about 1.5 centimeters a year. So it's more or less the opposite to what we observe here in South America. The subduction velocity for both subduction systems is the same, about 7 centimeters a year, but in one case it's the plate boundary that moves, that accommodates subduction. In the other one, it's the subducting plate that moves and accommodates the subduction. So why is this the case? Another thing you might notice, if we look at the topography at these two subduction zones, in the overriding plate here in South America, we see a massive mountain belt. We see the altiplano about 4 kilometers above sea level, and we see mountains up to about 7 kilometers in height. Now this mountain belt has been formed by basically crustal shortening and thickening and compression, producing high mountains. If we look at the Scotia region in the Southern Atlantic, we don't see a mountain belt, we see a basin, a backyard basin, which sits about 4 kilometers below sea level. And so the question is, why is this the case? Now this backyard basin here formed, as geologists and geophysicists have measured, basically formed by extension and stretching of the crust. So the question is, why do we have different kinematics and why do we have different topography at these subduction zones? Well, that's one thing I've been investigating for the last 8 years or so with my colleagues and students. And this should have been looping, as it did initially. What we see here is a numerical model of a subduction zone. This one represents a subduction zone that's relatively small, and I'll show you a movie of another one that's relatively big. What my colleagues and I proposed over the last 8 years is that the size of subduction zones that trench parallel extend is of great importance in the kinematics and dynamics of these subduction zones. So what we see here, we see a subducting plate and a relatively small subduction zone. And we see that as it sinks, the plate boundary, which is indicated by these dark colors here, black and dark red, the subduction plate boundary is moving backward with time, whilst the plate itself is only very slowly moving towards the trench. So this is very similar to what we see in the Scotia subduction zone. Subduction is mostly accommodated by the plate boundary moving backward. Now if we go to the next slide, here we see a movie of a very big subduction zone. So this is similar to the South American subduction zone. And what we see here in the middle of the subduction zone here, in the center, we see that the plate boundary is more or less fixed in space. So that's the dark red, black region. The plate boundary itself is more or less fixed in space, but the subduction zone plate, the subducting plate, is moving very rapidly towards the trench. So this is more or less what we see in the South American subduction zone, with the Nazca plate, the subducting plate, very quickly moving towards the east. So this explains to some extent the kinematics, and I guess one of the reasons why this was only done in the last 8 years or so has to a large extent to do with the computational power that was required to run these models. Okay, so here we see some slides, 4 slides, illustrating the relation between subduction zone size and velocity. Here at the bottom we see the numerical models, at the top we see the observations. The horizontal axis we see the size of the subduction zone, and the vertical axis here we see subducting plate velocity, and here we see the trench velocity. And we see that with increasing subduction zone size, the subducting plate velocity increases, scaling roughly with the cubic root of the square of the subduction zone size. And for the trench velocity, the plate boundary velocity, we see the opposite. With increasing subduction zone size, the trench velocity, the plate boundary velocity decreases, following more or less, scaling more or less with the inverse of the subduction zone size. So this explains the kinematics. But what about the formation of mountains or basins at subduction zones? Well, as I said, very big subduction zones sink more or less with a relatively fixed subduction zone plate boundary, and this induces polar order flow in the mantle wedge. Now, as it creates this stirring in the mantle, the plate, overriding plate at the surface, is basically being dragged towards the subduction zone, but the subduction zone itself is more or less fixed in space, and so the overriding plate bumps into the subduction zone and forms a massive mountain range like the Andes. The opposite, if we have a very narrow subduction zone, we generate very minor poloidal flow here in the mantle wedge. So poloidal flow is not very well developed, but in this horizontal slice you can see that we have very significant toroidal flow. Now this toroidal flow provides a drag to the base of the overriding plate, as we see in the top diagram here. It basically stretches the overriding plate apart, and it creates very minor stresses here at the plate boundary. So the plate is being stretched apart, and it forms a back arc basin. So I guess I can conclude now that subduction zone size matters in geodynamics and tectonics. For small subduction zones, we get very fast trench retreat, we get slow plate motion, we get toroidal flow in the mantle. This stretches the overriding plate apart, and we form a basin like here in the Scotia Sea, 4 kilometers below sea level. At big subduction zones, like the South American subduction zone, we have very slow trench retreat. We have fast subducting plate motion towards the trench. We create poloidal flow in the mantle, and we form a large mountain range by basically shortening the leading edge of the overriding plate. And I'll leave it there. Thank you very much.
Thomas.
Thomas Marshmeyer, University of Sydney. Very interesting talk. What defines whether it goes to be a small or a large subduction zone? You may have said it, but I may have missed it. Is there what are the criteria? Why doesn't it become small, or why does another one become large, given that more or less the same phenomenon happens?
Yes, well, at the moment, I guess it's a given how big subductions are. It basically has to do with the evolution of the tectonic plates. Some big subduction zones might segment and start to, break apart and form smaller segments. This might be related to different plate boundaries meeting at the subduction zone and therefore stopping subduction. And you might also have smaller subduction zones growing laterally and then combining into forming a bigger subduction zone. So it has to do largely with the history, I guess the plate tectonic history of the system.
Andy.
Thanks, Wouter. Andy Gledo from the University of Melbourne. It's a bit related to the last question. Do you see a mechanism whereby the small subduction zones, the limited length, can evolve into large ones? So I'm particularly interested in what might happen in the Atlantic as the Lesser Antilles arc and the Scotia arc have broken through from the Pacific into the Atlantic. Can they colonise the whole of that ocean?
It depends somewhat on the specifics. There's some subduction zones that form at passive margins, and you might initially form a small subduction segment. And if there's enough force available, this might grow laterally. And then passive margins can be 5,000 kilometers long, for example, and then it can grow 5,000 kilometers. At other settings, growth might be limited by other plate boundaries, like the Scotia Sea. It's bounded by major transform faults, which won't allow lateral growth. So this one most likely won't grow very much. So yeah, again, it's related to the specifics of the situation, I guess.
On that note, could you please join me to thank Professor Schellart?